Okay, good day. This is Pre-Calculus, and I am Mr. McCulley, and this is our continuing lesson on probability. This is part two. I'm not going to spend a bunch of time rehashing all of the notes because they are the same. We did them all in the first lesson. I just have a bunch of um, sample problems that I'd like to go over with you for this lesson. But we do want to talk about things and talking about probability of mutually exclusive events and independent events because we are going to be dealing with some more complex versions of those. So just real quickly, if two events are mutually exclusive, then they come from the same sample space. And the probabilities, you are going to add those two probabilities. If they are not mutually exclusive and there is some overlap, you have to subtract away the overlap. All right. The other thing is that if you have two different events, and they're not necessarily independent events, but we are talking about them. If there are two events going on, then what you're going to do is you're going to multiply those probabilities. So my first example here is kind of trying to show you how to distinguish between those two and make the decision of when you multiply and when you add. All right. So here's my first thing, and I've just made up a game. In a game, there are 10 marbles that are in a bag. 2 of those marbles are green, and 8 of those are blue. It costs $1 to play. If you get a green marble, you win $2. If you draw both green marbles, you win $10. And if you draw 2 marbles, well, then you lose. All right, so the first part here, part A, says, what is the probability that you win $10? Now, what that means is that you're going to draw 2 green marbles. So this thing is what is the probability of 2 green? All right, well, 2 green ends up being 2 separate events. Now, they are not independent events, but they are 2 separate events. All right, and those 2 separate events are going to be probability of the first one green times the probability of the second one green. Now these are not independent events because I'm going to keep that green ball, that first green ball out, and I'll have less balls in the bag, which changes the probability. So here there are 2 green balls in the marbles in the bag, and then there are 10 total. For the second draw, though, you've already taken out one of the green marbles, and there are only 9 marbles left. So the probability that you're going to draw 2 green is going to be 2 over 90, which is 1 over 45. So you've got a 1 in 45 chance of winning the $10. Part B says, what is the probability? I don't know why I did that. What is the probability that you win $2? So it says here at least 1 green. Now, this one is a little bit different because we could draw 1 green, 1 blue, or you could draw 1 blue and then 1 green. Now, there is no overlap here, but these probabilities are mutually exclusive of each other, and they are in the same sample space. So in this case, we're going to calculate the probability of this one and the probability of this one, and they're 2 separate events, but we're adding those probabilities because they are 2 mutually exclusive events inside the same sample space. Drawing a green on your first one would be 2 out of 10, and then drawing a blue one on your second would be 8 out of 9 because we've already drawn that. Plus, to that, you're going to add the probability of drawing a blue on the first, which would be 8 out of 10, times drawing a green on the second, which would be 2 out of 9. All right. So we end up with 16 over 90 plus 16 over 90. That's 32 over 90, which would be 16 over 45. All right. And then finally, what is the probability that you lose? Well, the probability of losing is going to be 2 blue. All right, so 2 blue here would be a probability of blue and probability of blue. So probability, the first one is blue, and then times the probability that the second one is blue. The first one blue, it'll be 8 out of 10. And then I will have taken one blue ball out and I will take one marble out. So it'll be 7 over 9, which will be 56 over 90. And then let's see here. If I can take a 2 out of both of those. So it'll be 28 over 45. I think that's right. That seems correct. All right. Now, here's kind of a check. We've done all of these. We've got all of our answers correct. And the point that I want to make about this whole problem here is that these are all of the outcomes. And since these are all of the possibilities, since one of these three things has to happen, if I go 1 over 45 plus 16 over 45 plus 25 over 40, or 20, what did I say, 20, 28, 28 over 45, I should get 1 because one of those things has to happen. Probability goes from 0 to 1. We've counted all of the possible outcomes. We should get 1. So we feel confident that we've done the correct calculations for that particular problem. All right, so my second example, a random number generator generates a 3-digit number consisting of digits from 1 to 5. What is the probability that the 3-digit number will be A, an odd number, B, all 3 numbers are odd, C, a number more than 4,000? Okay, so first off, let's talk about total outcomes. If our 3-digit number can only have 1 through 5, so 1, 2, 3, 4, 5 is 5 digits, so the total outcomes are going to be 5 to the third, which is 125. All right, so this first one, what does it take to have an odd number? To get an odd number, the last digit must be odd. As an example, I can have 4, I could have 4, and I could have 3, and that's still an odd number. So 443 is an odd number just because the last digit is odd. I can have anything here. It doesn't matter what those values are. So my probability of an odd number is going to be, I know I have 125 total outcomes because I've already calculated that, but I have 5 possible outcomes for the first digit. I have 5 possible outcomes for the second digit, but from 1 to 5, 1, 3, and 5 are the only odd numbers, so I'll have 3 there. And so 5 times 5 is 25, times 3 is 75, so I have 75 over 125. So let's see, 25 goes into both of them, so I have a 3/5 chance of it being an odd number. Now, that's not the only way to calculate that, but that gets us pretty close. So all 3 numbers are odd, so the probability all 3, well, this number would not count in our favorable outcomes because I have even numbers in there. So to get only odds, there are 3 choices for the first one, there are 3 choices for the second one, there are 3 choices for the third, and it's still over 125. And so 3 times 3 is 9, times 3 is 27 over 125. Now, 125 only has factors of 1, 5, 25, and 125. And this only has factors of 1, 3, 9, and 27. So that is going to be the last thing. And so a number that is more than 4,000, well, if it's a 3-digit number, there is the biggest number that we could have here is 555. So there is 0 probability more than 4,000. Well, that's going to just be 0. All right, last one. Example, the probability that Mr. McCulley will run on Monday is 0.05. On Tuesday, that probability has dropped down to 0.25, and then on Wednesday, it is only 0.1. What is the probability that he will run on every day? So I would have to, these are all 3 different events, and running on the first day does not affect running on the second day or the third day. So the probability of running all 3, well, that's just going to be the probability of Monday times the probability on Tuesday times the probability on Wednesday, which will be 0.05, or no, excuse me, it's 0.5. Probability on Wednesday is 0.5 times 0.25 times 0.1. I'm not even going to guess at that. So 0.5 times 0.25 times 0.1 is 0.1, so 1.25% chance, 0.0125 that I will run on all 3 days. That's not very good. So B, what is the probability that he will not run on any day? Okay, well, probability not run on any day will be the probability of the complement of Monday times the probability of the complement of Tuesday times the probability of the complement of Wednesday. So if the probability that he will run on Monday is 0.5, then the probability that he won't run is also 0.5. The probability that he runs on Tuesday is 0.25, then the probability that he won't run on Tuesday is 0.75. And if the probability that he will run on Wednesday is 0.1, then the probability that he won't run on Wednesday will be 0.9. And again, I'm not going to even try to do that in my head. So 0.1 times, or 0.5 times 0.75 times 0.9 is 30. So I got a lot of stuff up. So the probability that he won't run, or that he won't run on all 3 days is 33.75%. 0.3375. All right. So what is the probability that he will run on at least one day? Well, here's the thing. The probability of at least one day is the complement of no running. All right. So if I'm saying what is the opposite of not running at all, that's going to be running at least once. All right. So what we're going to do, instead of trying to calculate all of those values, the probability of at least once, that'll be the probability that is the complement of no running. And so we'll just go 1 minus 0.3375, 1 minus the answer, and 0.625. So there's a 66.25% chance that Mr. McCulley will get off his duff and run at least once during those 3 days, which isn't too bad, I suppose. Well, that's all I got for today, folks. So, in Empire Strikes Back, kicks off on an ice planet on Hoth, which was shot partially on location at the Pre-Calculin Glacier in Norway. I tried to pronounce that well, but maybe you could find a better pronunciation. Have a good day, folks. That's all I got. Bye.